Welcome to G Fun Facts Online. Picture an Earth completely alien to the one we inhabit today. From the vantage point of space, the familiar swirl of blue oceans and green land masses is entirely gone, replaced by a blinding, glaring sphere of unbroken white. The continents are buried beneath glaciers kilometers thick, and the world's oceans are sealed beneath a colossal shell of ice. The equator, usually a belt of sweltering tropical humidity, is a frozen wasteland with temperatures plunging to -50 degrees Celsius. This is the Cryogenian period, an era lasting from roughly 720 to 635 million years ago, during which our planet experienced the most extreme climatic catastrophes in its 4.5 billion year history. For decades, the Snowball Earth hypothesis has captivated geologists, climatologists, and evolutionary biologists alike. It provides a dramatic and elegant explanation for the bizarre presence of glacial deposits left behind at what were once tropical latitudes. Yet, this apocalyptic scenario has always harbored a glaring, irreconcilable paradox. If the Earth was entirely sealed in ice for millions of years, cutting off the oceans from the sun and atmosphere, how did light-dependent, oxygen-breathing life survive? Today, we are diving deep into the groundbreaking discoveries that have begun to crack the ice of the hard Snowball Earth theory. A sweeping reassessment of Neoproterozoic glaciation is currently underway, driven by high-resolution geochemical data, advanced climate modeling, and astonishing fossil discoveries. The emerging picture is not of a dead frozen wasteland, but of a highly dynamic slushball Earth, a world punctuated by vital oases of open seas, vigorous ocean circulation, and mid-latitude refugia that served as the crucibles for the evolution of complex life. To truly understand the magnitude of this current reassessment, we first need to look at how the Snowball Earth hypothesis was born. The geological breadcrumbs pointing to a frozen antiquity have been accumulating since the mid-20th century. That is when geologists began discovering dropstones, which are massive boulders carried by glaciers and dropped into marine sediments, resting in rock formations that magnetic data proved were located near the equator at the time of their deposition. In 1992, Caltech geobiologist Joseph Kirschvink coined the term Snowball Earth. He proposed a fascinating mechanism by which the Earth could actually freeze over completely, something known as the runaway ice albedo feedback. Here is how it works. When the ancient continents clustered near the equator, they became subject to heavy, continuous rainfall. This accelerated the chemical weathering of silicate rocks. This chemical weathering process acts like a planetary vacuum cleaner, pulling massive amounts of carbon dioxide, a potent greenhouse gas, directly out of the atmosphere. As the carbon dioxide levels plummeted, the Earth cooled, and polar ice caps began to expand. Because ice is highly reflective, meaning it has a high albedo, it bounced more of the sun's energy back into space, which cooled the planet even further. Once the ice sheets advanced past a critical threshold, roughly around 30 degrees latitude, the feedback loop became virtually unstoppable. The ice marched rapidly toward the equator, enveloping the globe. Harvard geologist Paul Hoffman later championed and expanded this theory, finding compelling evidence in the cap carbonates of Namibia. These are thick layers of limestone that sit directly atop ancient glacial deposits, recording the rapid, ultra-greenhouse aftermath of the snowball's eventual thaw. Under this canonical hard snowball model, this deep freeze occurred at least twice during the Neoproterozoic era: the Sturtian glaciation from roughly 717 to 660 million years ago, and the Marinoan glaciation from roughly 640 to 635 million years ago. During these cataclysmic events, the oceans were thought to be entombed under ice up to a kilometer thick, entirely shutting down the hydrological cycle, halting air-sea gas exchange, and turning the global ocean into a dark, oxygen-deprived abyss. But the elegance of the hard Snowball Earth theory clashed violently with the biological record. By the time the Sturtian glaciation began, Earth was already teeming with life. While animals had not yet evolved, the oceans were filled with diverse communities of bacteria, archaea, and crucially, eukaryotic organisms. These included photosynthetic cyanobacteria and early forms of green and red algae. Photosynthetic life inherently requires sunlight, and sunlight simply cannot penetrate a kilometer of solid marine ice. Furthermore, aerobic eukaryotes require free oxygen to survive. If the oceans were entirely cut off from the atmosphere, the dissolved oxygen would have been rapidly depleted by the decay of organic matter, leaving the seas totally anoxic and rich in dissolved iron. Under a strict hard snowball model, the planet should have experienced a mass extinction of catastrophic proportions, wiping out the ancestors of all modern plants and animals. Yet, the fossil record shows no such mass extinction. In fact, life emerged from the Cryogenian period seemingly invigorated, leading directly to the Ediacaran biota, which was the Earth's first flourishing of macroscopic, multicellular organisms. So how did these organisms survive tens of millions of years in a planetary freezer? Early attempts to solve this puzzle invoked extremophile behavior. Some scientists suggested that life clung to the margins of volcanic hydrothermal vents in the deep, dark ocean, though this obviously could not explain the survival of light-dependent algae. Others proposed that meltwater pools on the surface of the ice, known as cryoconite holes, darkened by wind-blown dust, could have hosted microbial communities. However, these tiny, nutrient-poor puddles were incredibly unlikely to sustain the sheer diversity of eukaryotic life that successfully navigated this glacial bottleneck. This profound biological paradox forced climate modelers back to their supercomputers. They asked a vital question: could the Earth have remained partially unfrozen? Thus emerged the Slushball Earth or water belt hypothesis. Using complex thermodynamic sea ice models, atmospheric scientists demonstrated that a completely frozen Earth is actually incredibly difficult to achieve, and, once achieved, even harder to escape. Some models suggested that as the ice advanced toward the equator, the extreme cold and the drastic lack of evaporation would fundamentally reduce global snowfall. Without snow to cover it, the equatorial sea ice would remain thin, bare sea glacier ice, which does allow some sunlight to penetrate. More intriguingly, several models revealed a Jormungand climate state, named appropriately after the world serpent of Norse mythology that encircled the Earth. In this specific scenario, the runaway ice albedo feedback is halted just short of total planetary encasement, leaving a continuous belt of open, liquid water churning right around the equator. This water belt would be sustained by ocean currents actively transporting heat from the equator to the ice margins. A slushball Earth would provide the perfect refugium, a sunlit, oxygenated strip of ocean where marine life could wait out the millions of years of glaciation. For years, the debate raged intensely between the hard snowball and the slushball camps. What was desperately missing was the physical geological proof from the rocks themselves that open water actually existed during the darkest days of the Marinoan and Sturtian glaciations. The ultimate turning point in the reassessment of Neoproterozoic glaciation came from the rugged, mountainous terrain of the Shenongjia Forestry District in Hubei Province, South China. Here, the Nantuo Formation holds an immaculate, continuous sedimentary record of the Marinoan glaciation, dating back roughly 654 to 635 million years. In 2023, a team of researchers from the China University of Geosciences, the University of Cincinnati, and the UK published a landmark study that effectively shattered the hard snowball paradigm. Buried within the dark, carbon-rich black shales of the Nantuo Formation, they discovered something that theoretically should not have existed: the fossilized remains of complex, benthic phototrophic macroalgae. In much simpler terms, they found ancient seaweed. The discovery of the Songluo biota, as these fossils are known, carried profound implications for our understanding of the planet. Benthic macroalgae live attached to the seafloor in shallow coastal waters. They are completely and utterly dependent on sunlight for photosynthesis. The undeniable fact that they were growing and thriving during the absolute height of the Marinoan glaciation proved unequivocally that their environment was not covered by thick, opaque ice. But the most shocking revelation was not just that open water existed, it was where it existed. Paleomagnetic reconstructions of the Earth's continents during the Marinoan glaciation placed the South China Block not at the balmy equator, but at mid-latitudes, specifically between 30 and 40 degrees north. If the equator-only water belt hypothesis were strictly true, those mid-latitudes should have been locked under solid, impenetrable ice. The survival of macroalgae in South China implies that Snowball Earth was not a monolithic block of ice with a single equatorial puddle, but rather a dynamic, shifting, and highly patchy landscape. As lead researcher Huyue Song noted, the The Marinoan glaciation was not a static deep freeze, but a highly active climate system, featuring multiple intervals of melting and freezing, creating widespread ice-free oases or islands of open water far from the equator. Now, fossils are incredibly rare, but the chemical signatures left behind in the rocks, known as geochemical proxies, provide a continuous broadcast of what the Snowball Earth oceans were doing. Recent high-resolution isotopic analyses have painted a highly vivid picture of these open-sea refugia. Let us look at the breathing ocean and the complex cycling of nitrogen and carbon. Under a hard snowball, the ocean's nutrient cycles would absolutely grind to a halt. Without wind to stir the waters, and without river runoff from the continents, the seas would stagnate. However, a seminal 2017 study analyzed nitrogen isotopes from Marinoan glacial deposits. Nitrogen is a critical building block for DNA and proteins. In a healthy ocean, the nitrogen cycle is driven by bacteria that fix atmospheric nitrogen, nitrify it in oxygenated waters, and denitrify it in deeper anoxic zones. The researchers found robust isotopic evidence of an active, complex nitrogen cycle during the Marinoan glaciation. This proves two monumental facts. First, there must have been significant air-sea gas exchange, which is physically impossible if the ocean is entirely sealed by a kilometer of ice. Second, the surface waters must have been oxygenated to support nitrification. The Snowball Ocean was literally breathing. It was producing marine oxygen, hosting an active biosphere, and maintaining nutrient inputs from exposed, weathering continental margins. While the surface waters in these specific oases were oxygenated, the deep ocean was an entirely different story. Without the global ocean circulation patterns we have today, the deep seas became highly stratified, anoxic, and ferruginous, meaning they were choked with dissolved iron. This intense stratification presented a unique survival mechanism, as outlined in a 2019 study examining iron-rich chemical sediments deposited in glacial environments. Scientists discovered that as the massive continental ice sheets ground heavily against the land, they produced immense volumes of subglacial meltwater. Because this meltwater was derived from glacial ice that had physically trapped atmospheric air bubbles, it was incredibly rich in dissolved oxygen. When this dense, highly oxygenated freezing meltwater discharged into the ocean at the glacier's grounding line, it violently collided with the warm, anoxic, iron-rich seawater. The dissolved iron instantly oxidized and precipitated out as rust, sinking to the seafloor and leaving behind the massive iron formations we study today. More importantly for biology, this continuous injection of oxygenated meltwater created localized, highly stable oxygen oases right at the very edges of the ice sheets. Even if the open ocean froze over temporarily, these coastal subglacial meltwater plumes provided a reliable, oxygen-rich sanctuary for aerobic marine habitats. Further corroboration of this dynamic comes directly from the dolostones of the Nantuo Formation. An intricate analysis of rare earth elements and trace metals in these specific rocks reveals a distinct chemical signature. The patterns conclusively show that while the deep waters were deeply ferruginous and incredibly toxic to complex life, there existed a persistent, thin oxic or suboxic layer, completely restricted to shallow coastal waters. These precise geochemical fingerprints definitively rule out the idea that the world's oceans were entirely poisoned or completely frozen. Instead, life was fiercely squeezed into a narrow, two-dimensional sliver of habitability, clinging desperately to the shallow, sunlit, oxygenated coasts of mid-latitude continents, surrounded by an encroaching ice sheet on one side and a toxic, iron-rich abyss on the exact other. Reassessing this Neoproterozoic glaciation not only solves the paradox of how life survived, but it brilliantly illuminates exactly why life suddenly became so complex immediately afterward. The traditional view of Snowball Earth treats it as an evolutionary pause button. The modern, dynamic open seas view frames it as an evolutionary pressure cooker. By confining all eukaryotic life into highly isolated, disconnected refugia, like those mid-latitude open water oases and subglacial meltwater plumes, the Marinoan and Sturtian glaciations created the absolute perfect conditions for allopatric speciation. Populations of algae and early single-celled organisms were physically cut off from one another for millions upon millions of years. In these intensely harsh, highly competitive, and resource-limited microenvironments, the selective pressures were immense. Organisms that could somehow cooperate, form multicellular colonies, or adapt to wildly fluctuating oxygen levels, had a massive distinct survival advantage. When the snowball finally began to crack, it did so with unimaginable violence. Millions of years of relentless volcanic outgassing had pumped atmospheric carbon dioxide levels to extreme heights, perhaps 10 to 100 times modern levels, purely because there was no liquid ocean or exposed rock to absorb it. Once the ice albedo feedback finally reversed, the Earth transitioned from a deep planetary freeze to a sweltering greenhouse hothouse in a geologic blink of an eye. The melting glaciers unleashed a planetary-scale flash flood, brutally scraping the continents bare and dumping millions of years' worth of pulverized rock, phosphorus, and other vital nutrients directly into the oceans. The isolated, highly adapted life forms in their coastal refugia were suddenly unleashed into a vast, nutrient-rich, rapidly warming and increasingly oxygenated global ocean. This is the exact environmental whiplash that scientists believe triggered the Ediacaran explosion and the subsequent Cambrian explosion, eventually giving rise to the first animals, sponges, and ultimately, us. Without the agonizing bottleneck of the open sea refugia, complex life as we know it might absolutely never have evolved. The massive shift from a hard snowball to a dynamic slushball or waterbelt model fundamentally changes our deeply held understanding of Earth's climate system. It demonstrates clearly that our planet has an astonishingly resilient thermostat. Even when pushed to the absolute extreme limits of cold, the Earth's internal heat, combined beautifully with the nuances of sea ice thermodynamics and oceanic heat transport, fights back continuously to maintain pockets of habitability. This profound realization stretches far beyond our own paleontology. It has massive implications for astrobiology. When astronomers search the vast cosmos for exoplanets, they so often look for Earth-like worlds resting neatly within the narrow Goldilocks zone. But the reassessment of the Cryogenian period strongly suggests that the actual parameters for life are so much broader than we ever assumed. If our own Earth could maintain open seas and support complex eukaryotic ecosystems while predominantly covered in blinding ice, then exoplanets previously dismissed out of hand as too cold or mere ice balls might actually be harboring vibrant, complex life in localized waterbelts or grounding line refugia. It also lends tantalizing, incredible hope to the continuous search for life within our own solar system, particularly on ice-encrusted moons like Europa and Enceladus, where dynamic subglacial oceans interface directly with tidal heating. The story of Snowball Earth is no longer just a simple tale of a frozen, completely dormant rock drifting through the void of space. Through the tireless, brilliant work of geologists reading the chemical signatures of ancient dolostones, paleontologists uncovering ancient seaweeds high in the mountains of South China, and climatologists modeling the intricate thermodynamics of sea ice, a breathtaking new narrative has confidently emerged. The Neoproterozoic glaciations were indeed the absolute most severe climate crises life on Earth has ever actively faced. But the beautiful truth is that the Earth was never completely defeated. Amidst the towering, crushing ice sheets and the roaring, frigid winds, the oceans kept breathing. In mid-latitude oases and equatorial waterbelts, beneath the glaring sun, patches of blue water rippled gently against the ice. Here, in these isolated open seas, the resilient ancestors of all modern plants and animals fought tenaciously for survival, transforming a planetary catastrophe into the ultimate crucible of evolution. The ice did not conquer life, it forged it. Thank you for tuning in to Fun Facts Online. Keep exploring and never stop wondering about the incredible history of our world.